In this video, we're going to take a look at forces, what they are, and some common kinds of forces that we encounter in physics. And we're going to take a look at how to draw something called a free body diagram, which can show us at a glance what forces are acting on an object. Now, why forces? Well, we've spent the first part of physics trying to come up with a common vocabulary and a common mathematics so we can all agree very precisely on how something is moving. Is it moving with a constant velocity? Is it accelerating? Is it speeding up? Is it slowing down? Is it at rest? So now the rest of mechanics is basically describing why objects move the way that they do. So if that thing is accelerating to the right, why is that object accelerating to the right? And the reason for that, any kind of motion, is forces. All right. So first off, what is a force? We don't need to get super technical here. A force is simply a push or a pull. All right. So something that pushes on an object or something that pulls on an object, that's a force. Okay. Generally, we have two main kinds of force. There's forces that act. Well, let's not even go that complicated. Let's say we have contact forces. And how come we're not? There we go. Contact forces. So these are forces that arise because two things are touching one another. And let's spell that right. We also have non-contact forces. So these are forces that can act between two objects that do not touch each other. They are not necessarily touching one another. All right. Contact forces, that's like one person pushing on another person or one person pulling on another person. I have to physically touch another object in order to apply a force to it. All right. Non-contact forces, these are the mysterious ones. And the big one that we're going to be dealing with this year is gravity. Okay. So I hold a ball up into the air and let's just go gravity. I hold a ball in the air and I drop that ball and it accelerates towards the earth. Why? Gravity. Gravity is a force that can act at a distance between the ball and the earth, and the ball and the earth do not have to be touching one another. Astronauts in the International Space Station and the International Space Station itself are attracted to the earth. And that force is gravity, and they don't have to be touching the earth in order for that to happen. All right. The other one that, depending on your physics class, you may or may not encounter would be the electromagnetic force. So let's go mag. So you know that two magnets don't have to be touching each other to exert a force on one another. And you maybe remember from chemistry class that something like two protons will repel each other because they have like charges. And they do not have to be touching each other to repel one another. A proton and an electron will attract one another, and they do not have to be touching each other to exert that force. So those are the two most common non-contact forces that we will encounter. All right. So if it's not gravity and it's not the electromagnetic force, for our purposes in Newtonian mechanics, then it's a contact force. And if it's a contact force, then something needs to be touching that object in order to apply that contact force. All right. So for us, we're going to be dealing with gravity in every situation. Right? So we take care of the gravity force, and then you ask yourself this question: what else is touching the object? What's touching the object? Those are the only things that can then be applying a force to that object. So whenever you're thinking about the forces acting on an object, ask yourself that question: what's touching the object? Okay, so now let's take a look at some common contact forces that we'll be dealing with in physics. So the first one is, well, first we've got a ramp here and a box sitting on that ramp. Okay, so again, we ask ourselves, what's touching the box? If I want to know what forces are acting on the box, ask yourself what's touching the box. Hey, the ramp is touching the box. Cool. That interface there between the box and the ramp, we're going to call that the normal force. Okay, so objects sitting on a surface experience that surface pushing up on them, or depending on what part of the surface they're pushing on. And normal forces is what we call those. Okay, so force normal Why is it called a normal force? Because in math, something that is perpendicular to a surface is called a normal. It's called normal to the surface. So that's why it's called a normal force. So that's pushing straight perpendicular to the surface. All right, all normal forces are going to push perpendicular to the surface. So if I had something resting on some sort of curved surface like that, then the normal force pushes straight perpendicular to the surface at that point. All right, and we give it the name F sub n, or sometimes I will call it capital N. I'm trying to get away from that because it gets confused with the unit for forces, which is a Newton, which we abbreviate with a capital N. So we're going to try and name those guys F sub n. Now, going back to my box on the ramp here, let's say it's at rest on the ramp. How come the box is not sliding down the ramp? Because there is a frictional force also acting between the two surfaces here, right? So again, the ramp has to be touching the box in order to apply a normal force, and then two surfaces also have to be touching if they're going to apply some sort of frictional force. Okay, so friction would be acting up the ramp here to oppose the box wanting to slide down the ramp. All right, so friction forces, generally I've gotten into the habit of using a lowercase friction, a lowercase f to label friction forces, but that is a common contact force between surfaces. All right, let's have some fun here and say that there's a little wall right here, and we have a string that is attached to the box. Okay, so these are called tension forces, and these are strings, ropes, chains, anything like that. The interesting thing about tension forces is that they can only pull, they cannot push. So this string is attached to the box, and it is pulling the box this way. Okay, and we call those generally tension forces. We abbreviate it as F sub t, usually, for the tension force there. All right. Boy, let's see. What other common forces do we deal with? Let's say over here we've got a box that is sitting on top of a spring, and that box is compressing the spring. Okay, so what does the spring do? The spring is pushing up on the box. All right, so we call this force spring. Spring forces can push or pull. If you pull a spring apart, then it's going to want to go back to its original shape, so it's going to pull back to its original shape. If you have a spring that can compress, and you compress that spring, it's going to, again, want to go back to its original shape and push. So spring forces can be pushes or pulls. Boy, what other kinds of forces do we commonly encounter in physics? Let's say we drop a beach ball, and that beach ball is going to accelerate towards the ground, and the air is going to resist that beach ball falling through it, and we call these air resistance forces or drag forces. So air resistance is synonymous with drag. All right, and we'd probably label that F sub AR or F sub D as the shorthand for drag forces. Okay. Boy, that's about it in terms of the really common contact forces. I mean, obviously, we can have people that are pushing or pulling on things, right? So usually we just call that a push force or a pull force. Yeah, so that we have kind of a common vocabulary here. When I say, hey, it's a tension force, you know what I'm talking about. Or, hey, it's a normal force, you know what I'm talking about. All right? So well, let's talk next about free body diagrams, because I've kind of started to draw free body diagrams on the objects here, but there are some pretty specific rules involved for drawing free body diagrams. Let's take a look at that next. So let's go back and revisit our box on the ramp, and let's talk about the forces acting on the object. Let's take care of the obvious one, gravity. And what's maybe not so obvious about gravity, especially in this case, is gravity always points towards the center of the Earth. All right, so this box is being attracted to the center of the Earth. So I'm always going to draw the gravity force going straight down. Okay, you might want to draw the gravity force acting this way, because you want to say that's why the box wants to slide down the ramp. That is not the direction that gravity is acting. All right? So please be careful with that gravity force. Always, always, always straight down towards the center of the Earth. Okay? Now, we also talked about the ramp pushing on the box, and we called that the normal force. So that is going to be right here. Force normal, I'm going to call it. And then let's say there isn't any friction on this ramp. So for right now, these are the only two forces acting. Okay, so what I have here is not technically a free body diagram. When we draw a free body diagram, usually we just have a dot that represents the center of mass of our object. Okay, so we are drawing a diagram to show all of the forces acting on this box. Okay, the dot represents the center of mass of the box. And we draw all the forces acting on it, and they always start on the dot and point away from the dot. That was not a very good straight line down. So on the dot, straight down, and label it. Okay? So gravity force. And then we've got the normal force acting between the box and the ramp, and that's going up at an angle normal to the surface, perpendicular to the surface. So I now have the two forces acting on the object. It's kind of called a free body diagram because this dot represents the box apart from everything else, and it just shows the forces acting on the box. Okay, these are not the forces acting on the ramp. These are the forces acting on the box, and the dot represents that. All right. Let's say that instead of the box being not subject to any friction, there actually is a force of friction acting on it, and the box is at rest because of that. So we're going to have, on this diagram, a friction force opposing the direction the box wants to slide down the ramp. So on the free body diagram, again, we're going to draw in that friction force going in the direction that it was going in this diagram, but the difference is it's acting on the center of mass of the box, that dot, which represents the center of mass of the box. All right? So in these diagrams, you should take care with the length of your vectors, and we're going to get into that more as we analyze how large these forces need to be, how forces interact to cause the motion of an object. We should also make sure that all of our forces have labels, appropriate labels. We've got to give them names. All right? And so F sub g for gravity, F sub n for the normal force, lowercase f for friction. That works for those. Okay? So here's another example of an object we're going to draw a free body diagram for. So we're going to draw a free body diagram for the forces acting on this box that's hanging from a spring, hanging from the ceiling. So again, I'm going to draw forces just acting on the box, nothing else. So we've got the gravity force that we took care of, and then we've got the spring force. And you ask yourself, what else is touching the box? Nothing. Then there are no other forces acting on the box. You already took care of the force that is the non-contact force, gravity. Then ask yourself, what else is touching the box? Boom. Okay, now I'm specific about this, and I'm hammering this what's touching the box thing home because there's a common mistake that people make. So let's say you've got a person standing on the ground, and in their hand they've got a ball, and they throw that ball so that it leaves their hand with some initial velocity. So now we're talking about a free fall problem, right? So the question is, what does the... Wait, hold on. Back up. Let's go back to the box because I actually didn't draw the free body diagram. Here is the free body diagram. That dot represents the box. We've got gravity going down, and we've got the spring force going up. Okay, there we go. All right. Now let's get to the ball. So what does the free body diagram for the ball look like when it's in the air? All right, so here is the dot that represents the ball while it's in the air. It kind of looks like a ball, actually. We take care of gravity first. And then we ask ourselves, while the ball is in the air, what else is touching the ball? All right, and you might say air resistance, drag. Air molecules are touching the ball. Okay, good. For right now, let's say that air resistance is so small we can neglect it. So then what else is touching the ball while it's in the air? What else is touching the ball? Okay, most people are going to draw in a force from the person's hand because they're thinking, hey, the person was touching the ball and threw it upward. That's the reason the ball's going up. That's the reason it's in the air. And they want to draw in like this force from the hand while the ball is in the air because without the hand, the ball wouldn't be flying through the air. I don't care, okay? The hand was touching the ball in the past. That's true. The hand was exerting a force on the ball while the ball was in contact with the hand. That's true. But the instant that that ball leaves the hand, then the hand is no longer applying a force to the ball. Okay, so while the ball is in the air, that's it. That is the only force acting on the ball, gravity, nothing else. Okay, so this is why I really, really, really want you to think about what is touching the object. Okay, if something is not touching the object, then it can't be applying a force to that object. All right, you guys are not Jedi Masters. I actually am a Jedi Master, so I can apply a force to something when I don't touch it. I will demonstrate that for you later this year. But for you guys, no forces if you're not touching the object. Okay, so don't make that mistake. So take care of gravity, then ask yourself, what's touching the object? All right, that's going to tell you what other forces are acting. Don't put in forces that aren't there. All right, that's it. See you next time.